All right. We are ready to start again for the last session of this second edition of Pi4AI. And we have a very special guest now. This will not be a session. This will be more of a lecture, I would say. And it's a real honor for me to introduce someone who I've just seen up until now on Google Scholar or YouTube. So Alfredo Canziani is a professor at the New York University. He has more than 2,000 citations on Google Scholars for his studies on machine learning and deep learning. He holds a PhD from the Purdue University. Alfredo, it's a great honor to have you with us. And a huge round of applause for Alfredo.
Thank you so much for having me here. So a few more words such that I can complete the advertisement. Yes, I am a professor, but I'm a teaching professor. So I have a YouTube channel where I put all my content available for free. Me and my assistant, Yann Lecourne, he's a French researcher that has been helping me with my course. When I cannot teach, he's covering for me. And he's working on his teaching skills. So again, we are online. We can, if you're interested in these things, you can check us there. Moreover, we are writing a book. I've been writing a book. He should be reading it eventually before we publish it, such that he can also join in the authorship on the first page. Meanwhile, since this stuff is not yet available, let me give you a small introduction about the things that this book might cover. So it's going to be a very, it's like a lesson. Well, it's actually 6 lessons put together in a 50 minutes presentation. So I will not go too much into detail, but let me share something of the basics of this field of deep learning, which is the basically engine that is behind, underneath all these models that you've been hearing about even today. So even today we have seen like there are so many models coming out every single day. There is like a disaster of papers you are supposed to read to be up to date. But then the foundations are more or less always the same. So my idea here is to actually give you some, at least some hint on how to learn how to fish instead of giving you the fish. Of course, you can go on Hugging Face and get all the fish that you want. You can grill it on the evening. But then if you would like to actually understand the next paper or the one that is coming next, you might need some foundations. And so I will try to share a little bit of foundations, starting from where we started with classification, which is the technique that is actually used to predict the next word in your sentence prediction, in your sentence generation when you use these large language models. So let's start from, again, classification. Eventually, we're going to get to conversation with transformers and so on. So why classification? So, I mean, I guess you already know about classifications. We're going to be talking about classification with neural networks. For this case, I'm going to be having a simple case. In this case, you can see there is like 3 different colors representing 3 different classes. And then we can actually show you the little points if I add some noise, so you can see the different 2-dimensional points. So the objective here is to figure out, given the coordinate, the horizontal and the vertical coordinate, that's going to be the input. It's going to figure out what is the color associated to that specific location. In this case, there are 3 colors, yellow, purple, and red. So if I use a perceptron, which is one of those models, actually the first learning model that we put together in 1957, there is a small issue with that. It's a linear model, and therefore all it can do, a linear model, is going to be just separating your data with linear decision boundaries. Now, what is the issue with separating non-linearly separable data points with linear decision boundaries? Well, yes, it's overlapping with your data, right? So there's an issue there. And so how do neural networks solve these issues? So the first approach, which is the one I prefer to see, is going to be basically undoing the spiral, right? So I thought that my neural network is simply undoing the spiral, such that my final classifier, which is still a linear classifier, can divide my data points with hyperplanes. this is an animation I did just undoing the spiral. It's not a neural network. I'll show you a neural network in a second. Usually, you are more familiar, perhaps, with this kind of alternative view, where you can see the decision boundaries are learning to figure out the curvature of my data. And so here you can see, as training progress, how the decision boundaries, again, adapt and warp around the data manifold. Let me show you for the first case where I'm undoing the data, the training data with actually a real case. So I'm going to show you a model here. So this model here is a pre-trained model. Can you see the model on the screen? Yes, you can. You can see I train a model. It has 2 input units because it's going to be reading a point on the 2D plane. It's going to have a 100-dimensional hidden layer. I have a positive part, also called a ReLU function. Then I project it to 2 dimensions, such that I can show it on the screen. And then I go up to 5, such that I can perform classification. So if you do that, and I show you now an input to the embedding interpolation, you're going to see what the network does to these points in order to be able to linearly separate them. So the network, in order to be able to linearly separate non-linearly separable data points, it will just warp the space that is what you're looking at right now, such that these points will end up in locations that are separated. It can be separated with hyperplanes, which is the final layer of the model. So here you can see there is some sort of stretching going on, and then eventually each color, each point of the same color will end up in a region that is separated from the other colors. And so what you're looking at is simply the neural network dewarping the input space into a space that is nicely organized, from which you can do a prediction if you belong to that specific region. And so here, once the animation stops, you can see what are the different regions that the model associates to each of these parts. So again, why are these regions separated by hyperplanes? This is my last layer. My last layer is the same layer as I showed you before. There are simply hyperplanes. And then how are these points come in this place, like in these locations? This is what the model did. It just warped this data. So this was an animation I show you from the point of view of a pre-trained network. I trained a network to just solve the classification problem, and I just send points into a trained network. So you can see what the dewarping function is doing. Let me show you another animation, which I made it just a few weeks ago, which is showing you something else. So this one, in this case, I'm showing you a network, the same network actually. Starting right now, it's not yet trained. So if a network, you just initialize it, how do you initialize your network? How are your weights of your just initialized network? They are random. They are large values or small values? Small values. So if you put something inside the network, what does it come out? If you multiply something with small values, kind of. That's what exactly you see. It's going to be just a small thing in the center. So now my network starts by outputting 0. Then I train the network. The first thing the network learns is going to be to actually increase the size. And until this point here, it almost looks like it learned the identity function. So the first part of the learning here, I spent, I think, 20 epochs to just learn to zoom in. So there is like a magnification part. Now that things are quite large, what it's going to be learning is going to learn to undo the spiral thing. And so as you look at this part here, the central part will rotate in a clockwise way. Meanwhile, the outside part will be turning in a counterclockwise direction. And now it's going to be performing a little bit more of a zooming until you get to the same final view that we saw just before. So this is going to be matching the previous one, which was just the same as the interpolation from the input to the output of the trained model. So these are the trained model. The one I showed before was the trained model. Previous video was the animation between the input to the output. The second video was the animation of the model that is learning. Okay? All right, so we just learned what these neural networks are doing. Are just doing some warping, interesting warping. How do we perform this warping? So let me show you how this works. So small recap. Again, you might already know these things, so I will go just rather quickly. But my computer is not happy. 1 second. Because I tried to do many things. Let's exit the full screen So my computer is going to be happy again. There you go. Yeah, OK, sweet. All right, so how are these operations performed? So we start with our input x, which were our two-dimensional data points that are going inside a first module. Then I have a hidden representation. And then it's going to be in another module. And then finally, I have my prediction, this y tilde. My y tilde is going to be something I'm going to be comparing with my y, which is going to be my target. So in this case, as you might know, the hidden representation is just a nonlinearity applied to the affine transformation of the input. And similarly, my y tilde is going to be some nonlinearity applied to the affine transformation of the hidden representation. And this nonlinear function can be the positive part, hyperbolic tangent, softmax, whatever you want. So here you have these different layers that are computed one after the other by taking all the inputs, multiplying by each input by a specific weight. Then you sum them up, you add the bias, and you apply the nonlinear function. You do the same for the second neuron. You're going to be taking all your inputs, multiply them by some specific weights that are the connection that are mapping those neurons to the second layer. You add some additional bias and apply some nonlinear function. You do that for all of them, you're going to get a lot of arrows over there. And all of these are going to be the weights for my first layer. To do the second layer, I do exactly the same thing. I will connect each point of the first hidden layer to the second hidden layer through a second weight matrix. And I keep doing that several times. And so here we have like basically a sandwich of linear operation, well, affine transformations, and then nonlinearities. You do a few of them, and then you get a network that is quite expressive and can perform any possible warping. So how is the warping performed? How does the network know how to unwarp my warped data? Well, we had to introduce a metric of how bad a specific performance is. And so we're going to be using, OK, well, one more summary slide here. So we have this different type of representation, which is a view that we like. So it's going to be the full system. So the full system here has two inputs. One input is going to be the x. Another input is going to be the y. Sometimes people call the y the output of the network. Well, I disagree. Both x and y's have arrows that are going inside my network. So my machine, in machine learning, has two inputs, one x as input and also the y as input. And then I use the y as a target to compare my own predictions. My prediction in this case is called y tilde. Why there is a tilde? Because it's like an approximation, it's like circa, more or less, trying to copy what is the y. How do I make my y close to my y tilde? Sorry, the other way around. How do I make my y tilde close to my y? Then I have that C box, that red box, that is representing a distance or a divergence or whatever you want to call it between my y and my y tilde. So the far away my y tilde is, and the larger this C is. So this is going to be the cost that my network pays for making a bad prediction. More math that is exactly the same as you've seen before, and more nonlinear functions that are similar to the one you saw before. The only interesting point here I want to make is going to be that you can think about this y tilde, the prediction, yes, is a function of the input, but the actual thing that actually really is a major point here is that you're mapping your input into a hidden representation that has to be much larger than both the input and the output. Why is the case? So if you have these very large hidden representations, things are very easy to move apart. It's very flexible. The model is very flexible, and the optimization process is pretty easy. It used to be the case that we didn't have hardware, we didn't have GPUs, we didn't play video games. And so back in the days, you had very limited resources. Therefore, you could only manage to train small neural networks. Small neural networks have small number of parameters. They are very unflexible. So even though you could have tried to train them, but unless you have many parameters, it's very hard for the optimization process to actually converge. And so that's why you're observing these models that are larger and larger and larger. Some statisticians were claiming back then that, oh, if your model has so many parameters, it's going to be overfitting and learning the noise. Well, we show them that if the model is even larger, it doesn't care anymore about the noise, and you have like a double descent thing. Some magic, black magic of deep learning. Anyway, so the point here, again, was the fact that we need this high dimensional representation to be able to smoothly pull things apart. Moreover, we can have another metric here. So C was measuring the distance of my prediction from my target. Now F, which is going to be exactly a C, but it's going to measure here the incompatibility between my X and Y. I will call this F the energy of the model. So I can express with the energy the incompatibility between my inputs. And in this, and we can define it as being the sum of all the red boxes inside the big box. In this case, this energy is going to be just equal to the single red box. So let's have a look, what is this Y tilde? So this Y tilde comes from this function here, that unfortunately too many people call it softmax. Well, they forget the arg, but well, I won't talk too much about that. Anyway, it's going to be just this expression here, the exponential of this last linear layer output, and divided by the summation of the exponentials. We define this loss, this calligraphic loss, that is basically the badness of my weights for my data set. And this badness of my weights for the data set is simply the average of this capital L. And the capital L is going to be the badness of my W for that specific XY pair. Okay? In our case, we make the decision to use as a loss the energy I showed you before, the incompatibility. So what happens if I want to make my X and Y more compatible? Well, if I want to lower the loss, is that what I'm trying to do? Okay? So I present some X and Ys from a training set. By trying to lower the loss, I will just make those X and Ys that I present to my machine more compatible. So that's all machine learning and supervised learning is about. Make the pairs that I show to you actually compatible. Okay? Finally, what is F equal? F was equal the sum of all the boxes. We only had one box, so here everything is equal to everything. So the loss equal the energy equal the cost. And some of my undergraduate students are complaining about, if everything is equal to everything, why are we actually introducing L, F, and C? Just to give you confusion. No, because we can basically expand. So F can be many more other boxes. If you have more boxes, F is going to become the sum of all your boxes. How about the loss? Can the loss be something else? Yes, we have so many different choices of losses. This is just the most trivial one. But we can have contrastive losses. We can have many types of other different losses. And so I just give you the ability of having additional degrees of freedom here. Anyway, for classification, everything is equal to everything, so we don't care. So I just mentioned, but again, for later work. In this case, we choose our cost, which is this distance between my target, the blue target, and the Y tilde is going to be this negative log inner product between the Y, which is a one-hot vector, and my Y tilde, which is this kind of probabilistic vector. And this is called either cross entropy or negative log probability, or whatever you want to call it. So this is basically doing maximum likelihood. If you don't know what I'm talking about, it doesn't matter. So, but how does it work? So let's make an example so we can understand. So if, let's say I have an X, which was one of my two-dimensional points, and then my Y is going to be this one hot target, representing one of the three different colors. Let's say my prediction is basically the same, 1, 0, 0, when the blue ball Y is going to be also 1, 0, 0. How much is going to be the cost that my model pay to make a prediction that is basically the same as the target? Well, if you compute the inner product, you're going to get a 1. Take the log of that 1. You're going to get a negative 0. You make a negative in front, you're going to get a 0, a positive 0. Okay? Is making sense? Yes? No? Okay, more or less. In the other case, if you fuck it up, and then your model is going to be telling you that the second class is the one that it believes it should be the true one, then again, how much is going to be the cost you pay for making that mistake? You do the inner product, you're going to get something that is going to be roughly 1. You take, sorry, roughly 0. Bit positive 0, you take the log of that number, you're going to get negative infinity. You make a minus in front, you're going to get a plus infinity. Although you might think, oh, my model will never completely be 100% wrong, well, maybe your labels are 100% wrong because you have people that are labeling your data that make mistakes, so you actually get these spikes. What happens if you get a plus infinity cost? Okay, the next slide. But things can explode, right? So that's why we clip gradients. Anyway, let me show you the last slide of this part of the story, the first part. So how do we finally train the network? How do we force the network to perform that specific transformation of my data, of my data space, my input space? So let me collect all those matrices and biases all together into my W vector, which is going to be my weight vector. Therefore, I have this loss, which is telling me the badness of these weights for my data set, training set, is going to be a positive number. And so you can think in this case as being function of a single scalar W. I have my loss here. On the axis, on the horizontal axis, I have my W. I start somewhere, so we initialize our network with a random initial location. I have a W naught there. I have some specific value for my loss over there. I can compute now the gradient or the derivative of this loss at that specific value. In this case, is the derivative positive or negative? You have to shout because I cannot hear what you're saying. Positive, right? Because it's going upward. And so if it's a positive derivative, where is the minimum? To the right or to the left? To the left. So I have to follow the negative derivative. And that's why I will, again, move towards the negative direction of the derivative, which is basically the direction of steepest descent, such that I can go downhill, and this is called gradient descent, which is the technique that we use to update the weights to find the minimum of your badness for the weight, such that you find the less bad weight or the optimal weight. How do we compute these derivatives? Well, you just apply chain rule. But since we are fancy, we're going to call this something else. We call this backpropagation. But again, chain rule can be enough for the moment, right? Then I have slides about backpropagation, which is like the smart way of computing the chain rule by saving, caching all the different things. But again, we don't care too much about this right now. And we're going to be going to the next point, which is the next set of slides. But the major point here was that we were able to process vectors of, like x is going to be a vector of finite length. So how can I process vectors of variable length? And so how can we process basically if x is like a sequence, how about processing different length sequences? There are different techniques that are allowing you to process sequences of variable length. One of these is going to be a network that has an internal memory, which is getting updated at every single time you observe a new element in your sequence. What I'm talking about? Well, I think you might already know the answer. The answer is going to be a recurrent neural network. This is the first, one of the architecture that was used to process sequential data. So how is this stuff working? So I'm going to show you some, again, similar diagrams to the one we observed, but in a slightly different flavor or configuration. So now we're going to be talking about how can we change our data, our network architecture to process some specific type of data. So we have some specific requests. So we start again with our X. In this case, it goes inside this first module, and I'm going to have my hidden representation as before. Now I take this hidden representation, and I send it through this specific zeta to the -1 unit. If you heard about Z transform, you might know what this Z to the -1 is. If you don't know what the Z transform is, it's okay, don't worry. Anyway, so this is going to be my unit delay. What does the unit delay do? If I put my current hidden representation H at the index T, what is going to be returned to me is going to be the H at the previous time step. And so basically this unit delay just keeps in memory your hidden representation for 1 unit of time, and then it returns it to you the next step. And so you send something in, you have to wait 1 clock, and then poof, it goes out. You send something in, you have to wait 1 clock, then it comes out, right? So these recurrent networks don't have really loops. They are just having like 1 clock later, you're going to get the thing back, right? So it's like a flip-flop if you're electrical engineers. If you are software engineers, you might not know what it is. Anyway, so the one question you might have, how about when I put my first hidden representation? What's going to be the 0, 1? What is H of 0? Well, we have to add there a additional initial value, right? So at the beginning, this stuff has to output something. We just can decide what to make it output. And so my system will either switch to H0 for the first time, for first prediction, otherwise it's going to be fetching the previous hidden representation and send it back. This is called a dynamic system in physics. It is a system that has memory of whatever happened before, a system that has an internal state that gets updated as you put a specific input. So if I put to a normal neural network one input, it's going to get the same output. Put a one input, I get the same output. It's going to be always the same thing. In this case, it's not. If I put one input, it's going to have one output. Now, if I put the same input to the model, well, my output might change because I have memory of what happened before. Anyway, so in this case, we can think about this as I feed in my axis, I will generate a specific trajectory of my hidden representations. Then I decode them, and I'm going to get a trajectory of y tildes, my prediction for the target y. How do I make my predictions close to my target? As before, I will introduce a cost, which is acting as basically a spring between my y tilde and y. So y is going to be my hinge, and then I have a spring that is making y tilde go close to the y. Why do I talk about springs? If you remember from Physics 101, and this is going to be, for example, a square Euclidean distance, like you take the square, you take a distance of something, you take the norm, you take the square. This is going to be the energy of what physical system? If you take the gradient, you're going to be getting the actual force, which is going to be the distance. The distance is going to be the spring. The spring is going to be the item, the physical item that is increasing the force linearly to how much you displace it from the resting position. If it is too much for you, just skip what I just said. Let's go to the second part. So how about we figure out some math, right? So I have these diagrams. I'm an electrical engineer. I usually draw diagrams, but some of you prefer equations, so there you go. We have some initial hidden representation. I have to initialize my internal state because we turn on the system. I have to say, oh, reset to some specific value. Then my next value for the hidden representation is going to be function of the previous state and the current input. Finally, at every time step, I will just generate my prediction as a decoding of my hidden representation. Now I have a question for you. How much is going to be the overall incompatibility level between my input x and y? Here in this case, x and y are two sequences. So what is the answer to my question? Maybe you can answer by the time we finish with the next slide, and we come back to this one. So let me show you in a more concrete manner what we did in the previous diagram, which was a recursive, software engineers, you might be familiar with recursion. Here we have that to come up with an output, you have to use this recursion because you put the output of your system back in your own system, right? Like your previous h comes from applying the same function multiple times until it gets to the first initial value. Anyway, so let me put here the equations and then give you like a time lapse of what happened here. So on the bottom side, I have all these different calls to this recursive function, 0, 1, 2, 3, 4, 5, and 6. At the beginning, we're going to start with this h at 0, which is going to be this h naught, the initial value for the state. Then I get my first x, the first item of my sequence, and I feed this initial state and my first input to this predictor, whatever, which is going to be returning my first hidden representation, which goes inside the decoder. It gives me y tilde, which I'm going to be comparing it against my target, the blue ball y. And in order to make it not fly away, I will hinge it on my target through a spring, which is going to be this C cost here. We can think about the square Euclidean distance. How about next? What do you do? Get the next sample from my sequence, my input. I feed it to my predictor inside the previous hidden representation. I get the current hidden. It goes through the decoder. You get a y tilde, this prediction, which again, you're going to be comparing against the second target through this second spring, such that things don't fly away. And you keep going this multiple times, you're going to get the idea of how does this work. And so my question now is going to be the same as before. What is going to be the level of incompatibility between my pink sequence and my blue sequence? So how much is going to be this overall system energy? the sum of all the boxes, right? So in this case, we can figure out that in here it was a little bit tricky because you only see a single box, but instead the correct answer is going to be the energy overall is going to be the sum of all the costs that you incur by making wrong predictions throughout the whole sequence, okay? And so this is basically how these recurrent networks are basic mapping sequences to sequences. So what are the 4 different options? You can do pretty many interesting things with this kind of architecture. The first one, which is going to be something you're very super familiar with, which is going to be your autoregressive model. You're going to provide a specific input, for example, a picture of a cute dog. You can ask your model, can you describe this picture? And so the picture, the model will spit out a specific word, and then you feed back your specific word. You're going to get a second word, you feed back the second word. You can keep going like that. You're going to be using a process that is called autoregressive, where you feed your own output back into yourself to spit out the second output. You do that several times, you're going to get your full sequence of towards the output here, the blue, the targets. And so this is called the vector to sequence, where I map a single vector to a full-blown sequential thing. Then, so this could be captioning, for example, of images. You can do also the reverse. For example, you could have several of these items, which could be the words that are describing an Amazon review. And then as a target, you have the single number of stars that a specific review had. And so this is going to be the reverse, where you map a sequence to a single vector. What next? Next is going to be something that is very, very, very interesting because it allows you to map different length sequences, although in this example here, unfortunately, I used the exact same number for the target and the source sequences, but this is actually what was powering Google Translate for a number of years when they moved away from statistical neural translation to from statistical machine translation to neural machine translation. And so here you just have an arbitrary length input sequence, like, oh, I'm hungry in English, and then you condense this sequence into a single vector, which is, you know, the meaning of your sentence, and then you're going to be decoding this into ho fame. But then, of course, ho fame is I have hunger. Meanwhile, the English is I am hungry. So you have 3 words. Ho fame is 2 words. Ho fame already capture who has fame or famine. I don't know how you want to call it, but hunger. So it's going to be different sentences, different auxiliary verbs. So you cannot do a one-to-one mapping. I cannot say I am hungry. Io sono, okay, you can say io sono affamato, but it doesn't sound, I don't think it's what you usually say. So you could do one-to-one mapping, but then it makes more sense to actually extract the meaning of a sentence and then try to reproduce that sentence in a different language without having this kind of, again, one-to-one mapping. And so we're going to be getting back to this in a second, which is going to be the sequence to vector to sequence, which is what actually got started the whole transformer revolution. And then the final one, which is something a bit weird, which is sequence of sequence mapping where the sequence have the same length. And so this is direct sequence to sequence. An example of this architecture would be, like an example, an application that is using this type of architecture would be basically defining what type of words I'm using in a specific sentence. Let's say I'm going to say the clear bottle. Clear could be a verb, adjective, or is it a noun as well? Sorry, I'm speaking Spanish now, many languages in my head. So you can have, you can basically try to predict what comes next. What is the objective you're looking at, right? Noun, objective, articles and so on. And so this is it's called part of speech tagging. Anyway, so I was going to talk about how to perform the bottom left-hand side, which is going to be the sequence, vector sequence mapping. And so this, again, was what was powering these language models. And so let's get to language models, and in this case specifically, the sequence-to-sequence modeling. So, for example, in this case, I will use the example of machine translation, which is, again, what got us to get to the transformer, but there are a few more steps before that. So, machine translation basically maps a source sentence to a target sentence. And of course, these two sentences have different number of words. So, for example, the source sentence could be, the front door is red in English. And then it has capital M different symbols. Then we could have, in a target sentence, the Italian translation, la porta d'ingresso è rossa. Or we can have a second target sentence, which could be 前面是红色的 if you speak Chinese, but usually my classes are 80% Chinese people here. I don't see anyone, so it makes no sense to speak Chinese with you today. Let's go with the Italian case. So on the left-hand side, how do we perform machine translation? So we're going to have, as my first part of my input, the front door is red. This is my first set of capital M symbols that I input to my system. And so these are going to be the embeddings associated to the source sentence. Then I feed this to this first recurrent model, which is going to give me this hidden representation that is basically condensing the meaning of the first sentence. And now we have to unpack this condensed meaning, which is like a concept vector, into Italian to translate whatever that sentence meant. And so here we have, as input to the second part of the model, is the still Italian sentence. For example, we have beginning, and then it's going to be la porta di ingresso è rossa. And then we feed this to our decoder model, which is going to be asked to perform what? It's going to try to predict the second word in the target language, in the target sentence. And so when I provide the B, which is the beginning of my translation, the model will be required to produce la. When I feed back this la to the model, my system will be forced to predict porta. When I feed porta, the system will be forced to predict D, and so on. And so every single time we are doing the next word prediction. This is called language modeling, when you just try to predict the next word in a sequence, and so on. Until when? When do we stop? Well, after we say la porta d'ingresso è rossa, we have the E, which is representing the end of sentence. So like over there, we know that we are done with the translation. And so how is this done? Hold on. Yeah, these are going to be the targets. These are going to be the identity of my next word that I'm trying to predict. And then, yes, that's what I was going to say. How to make sure the prediction actually goes there. So I have a cost for every word, such that I try to, as we said before, try to get these predictions as close as possible to my target. And so here we have this bunch of C's that are these springs that are trying to make the predictions, again, close to the specific sentence. How about we change language? To change language, you're going to be providing a different source. For example, again, we have the Chinese version that you might not be able to read. And then on the other side, we're going to have exactly the same. We're going to be having the identity of the next word in the sentence. And until we reach the final end of sentence. Cool. So this was actually working and made a very huge leap forward for translating text at Google. That's why the whole corporation decided to switch techniques for their translation system. But then there are some limitations here. There are three major limitations, which are what prompt us to develop first attention and then eventually the transformer. And so basically get into the architectures that we are using these days. So first of all, there is nearby context bias. What does it mean? We have this HM, which is the condensed version of my sentence, which is the final state of my system. And so the final state of my system will reflect mostly information that has been seen towards the end. Do you remember the first word I said at the beginning of this talk? No. Do you remember what I said just right now? Now, exactly, right? So exactly, you have the same. I know it's the last talk of the day. You're kind of going to sleep, but I try to be, entertaining as much as I can and keep you awake. But the most, you have this towards the end bias. You're going to be remembering mostly what I just said right now rather than what I said at the beginning. So this is first issue with these recurrent, recursive models. The second one is going to be the fact that you have a fixed amount of cache in your brain, right? If I keep talking all the time, eventually something will spill out and then you're going to be forgetting, right? And so this is a major second issue, is the fact that your concept vector has a finite capacity. So if I have a small sentence, maybe you can capture the meaning of that sentence. If I keep talking for a whole hour, it's harder for you to capture the whole meaning of the whole lesson in the same amount of, single unit. These are two major limitations. And then the third one, which is something my friends in the hardware side are complaining about, that recursive stuff sucks. Because you cannot parallelize something that depends on the previous iteration. And so we're going to be seeing how we can address each of these three items with attention. Before doing that, just because I have these slides from my undergraduate course, I will share with you what matrix multiplication is, because sometimes you might forget. And some of you has, and so I'm going to be going over this, although my results somehow could be offensive, but whatever. All right, so what is this stuff? So we usually use the symbol on the left-hand side, which is this very kind of very convenient way of expressing the big thing on the right-hand side. But what is the actual meaning? So most of you will remember what is the actual implementation details, so you can code this up. But the fact that you can code something up doesn't mean you actually have understanding of what you're doing. You just know how to procedurally compute those numbers. And so, again, let's start with the one that you're most familiar with. Is going to be this row times column multiplication, where you multiply these n-dimensional vectors together. So you do inner product, scalar product, dot product, whatever you want to call it. And so here you end up with m inner products of x towards each of the rows of this A matrix. So you can think first of this matrix vector multiplication as the projection of your input vector against each row of your matrix. If you have m rows, how many projections you have? M. You project the single input against all of those, right? So this is the first one. Keep it in mind. We're going to be using it in a very quick moment. So first, projection of single input towards all of those rows. Second one, which is actually where the matrix vector multiplication definition comes from. I have here n column vectors. Each of these vectors have height m. There are m components in this vector. So when I perform matrix vector multiplication, I'm simply performing a weighted sum of the columns of the matrix A scaled by the coefficient in the vector x. And so guess what? If each of these vectors are size m, and you take the sum of them, what is going to be the output of this operation? Say again? M, right? So if these are height is m, you take an average of things of size m, m comes out, right? So it's not possible for you to get confused what is the output of performing what is the m times n. Like, if you want to map a matrix, if you want to map a vector to the n space to the m, you cannot be confused in what is the size of the matrix, m times n or n times m. Of course, I said every possible combination right now, but then if you just think about the fact that you take this matrix vector multiplication, take just the kind of weighted sum of the columns, then it has to be the size of the column, the size of the thing that you send in the output. Okay, this is the second one, so this is going to be the weighted sum of the columns. And then there is the third interpretation I'm going to use also today. It's going to be some sort of linear transformation. So if I perform a matrix vector multiplication and my matrix is a square matrix, it's going to be just rotating points in some space. Why do I talk about that? Because in 2 dimensions, you can change length in one way, you can change angle in one way. In a 100-dimensional space, I can change length in one way, I can change angle in 99 dimensional ways. And so basically in any high-dimensional space, things are just rotating stuff around. And so these are the 3 operations, either projections, weighted sum, or rotation. Okay? Let's move forward with attention. I'm going to use all of these three, bless you, things. So here, we're going to be talking about sequence-to-sequence model with attention. This is made by my coworker, Kyung-Yoon Cho and Yoshua Benjo. And of course, the PhD student was Bak Nadao. It was 2015 when we introduced these attention things. So attention allows us to perform something called context-based summarization. So this allows me to get a summary that is going to be context-dependent, as you can imagine from the actual noun. So the recurrent network without attention, we have seen just before the equation. Now instead, the one with attention has an additional input. So I have the previous h, the previous state. I have the current input, my x. And then I have this context, c, which is going to be different for every time I provide a different input. So how do we compute this? So we have here some symbols that are going to be a little bit cryptic unless I tell you what these are. So I have this capital S is going to be just the collection of all these S's. What are these S's? These are the output of my encoder that is being fed with my source sentence. And so these S1, S2, S3, so on, are the hidden representation of my encoder when I provide my source sentence. So I take these vectors, 1, 2, 3, 4, 5, whatever, and I stack them all. So then I have a matrix. What is the number of columns? 5, I count. 1, 2, 3, 4, 5. And then what is the height? Whatever the height of these S's, right? So if I take this matrix and I flip it, so before we had columns, now you can have rows, right? I take all these rows and then I have my H here, my previous H. If I do matrix and vector multiplication and I do what's going to happen? You just do the projection of your previous hidden representation against all the source hidden representations, right? And so these R's are the scores, the projection of my previous state against all these hidden representation from the encoder. So far, some of you already gave up before sitting down, but okay. I'm covering 6 lessons in 15 minutes. I don't know how much time I have left still. Anyway, so let me finish here. We have this, finally, I have to compute this context, which is going to be, again, the output of this, again, matrix vector multiplication. What is the meaning of the stuff? And so, first of all, I have to tell you this A is going to be coming out from this soft argmax, which is the function I even showed you before, that exponential divided by the sum of the exponentials, which is basically converting my scores, R, these projections, into basically a probability. And so if A's are basically probability elements, and I do this S times A, this is the second representation. We said that the matrix vector multiplication was the weighted sum of the columns. And now the coefficients are these numbers A here. These are the attention coefficients. So I'm going to be taking the weighted sum, well, actually, it's going to be a weighted average of my columns, those S columns, based on these weights that are computed here. So the interesting thing here is that these weighting coefficients are computed based on what? The previous representation and all the source hidden representations. And so this weighted sum, so when you call a weighted sum, what is a weighted sum? You have a sum with weights. But weights in machine learning are things that you learn with gradient descent and backpropagation. Instead, these are different weights. These are called fast weights. There are weights that are computed during inference. Again, if you didn't understand what I said, just, okay, let's move forward. All right, so now we took the average. The main point here is that I have my source sentence. There's a summary of the slide. You have the full source sentence. You send it through the encoder. You're going to get S1, S2, S3, S4, S5, blah, blah. These are the hidden representation of the encoder that I feed my source sentence, and now I take the average, okay? If my attention are all 1 divided by capital M, I just take the average source hidden representation. Now, if my A's are not all equal to each other, but they are a bit different, I will just focus on a different input representation, okay? You can just take either the average or you take something with more weight. So you can take a weighted average. So attention is just a weighted average. Okay, let's repeat all together. Attention is a Weighted, oh, amazing, okay? So that's all it is. And the weights are fast weights because they are computed at the inference time. Sweet. So we can do this, amazing. Attention has no weights, just fast weights. And it supports variable length sources. Why? Because if you take the average of 5 items, or you take the average of 7 items, or you take the average of 2,037 items, it's still an average, right? It doesn't matter how many items. You just take the average and you just make it a weighted average. But attention is just an average. All right, so let's do this. So we're going to be taking here our sentence. The front door is red. I will encode this when I have all my S's that are the source hidden representation. Now I start with my target sentence, which was the first word was the beginning, and then la porta d'ingresso è rossa, eccetera, quello che è, whatever it is. And now what do? So I have to force my system to output at the beginning the second word, which is la. Given that I feed la, I want to output porta. Given that I have porta di ingresso and so on, right? So one word at a time. And so how do we compute that? Well, we feed this to my decoder. I have a hidden representation, initial state. But now, I want to make this white tilde close to my first word. But I need one more information here. I need to compute. I don't know what's happening anymore. I don't see. Oh, what's happening? Hold on. Is it moving? No, it's not moving. Oh, yeah. Oh, no, yes, I didn't see the lines because, of course, sure, it's very fainted here as well, okay? So here I just do the projection of my hidden representation against all the previous ones, so I have all these scores. Then I convert them to probabilities, and you have basically the first way, that is the one that is only be looked by the target la, is going to be the. So the is going to be almost entirely looking at the. Can you guess why it's not exactly correct what I just said? How can you translate the in Italian? Il or la. Therefore, the attention for producing la should have also some weight pointing towards door, which is actually 2 hops in the future. And so as you can tell, this visualization is a fake visualization for educational purpose only. And I made a new visualization with the actual transformer, which is showing you that in order to translate from English to a gendered language, the actual prediction of articles will look at the noun as well to determine the sex of the articles. Yes, Italian is sexist. It has sex in the language, right? All right, anyway, so eventually, pretending that we translate the with la, we have that the first context-based summarization is just focused on the first word. And so you can see that S5, which was the final hidden representation for the source language, was mostly focused maybe on red. And so the first source, S1, the first source hidden representation is the one actually that mattered the most to make the translation of to come up with the first word from my translation. And then, so that's where we source it. Then we do the same for the second. So I do all these projections. And there we have that porta and porta di entrata, porta di ingresso, no? La porta di ingresso has to look at both these 3 words. We look at the front door, because front door is an adjective, but we don't have the front door in Italian. We have the porta di ingresso, okay? What's next? Well, next we have to fix the last problem, right? So we had one more problem, which was the fact that this stuff here still requires you to produce the previous output to feed it back to this next cycle, right? We have this internal state that updates at every instance. And so this is a disaster for parallelization because you have a dependency graph, right? And so finally, the last part is going to be how to get rid of these recurrence. Well, just throw the recurrent network outside the window and just use attention. So attention is all you actually need to get this stuff to run. And so let's see how it works. So it turns out that self-attention is a technique for dealing with sets, okay? It's not sequence, it's sets. What's a set? A set is going to be a bunch of things. It's like a bag of items. There is no order. You can shake them. It's the same set. And so here I have an X inside my curly brackets X. I have capital M of these X's. I can put all together. I can stack them up, and I have this capital X. I have capital M columns, but then there is no order. I can flip things inside, still the same thing I have. So I have this guy here, and I pick one of these X's. I put it here on the right-hand side. Then I put the big X to the left. And here I have all these X's. All right, cool. So what do we do here? So first of all, we're going to be asked a question. We compute a question by rotating my X with this WQ matrix. So this is first generation of a question. Now that I have a question through that matrix multiplication, I'm going to be getting my Q here as my output for question. Next, I'm going to be generating some keys by rotating each individual X with this WK matrix. Guess what? If you press Shift, you keep typing, you just get all capital letters. Which is basically, if you do matrix vector, you just stack multiple vectors, the output is going to be just the same, multiple outputs. Okay? So that's why if you put capital X afterwards, the matrix, you can just get capital K. Let me drink 1 second of the water. Do we know how many minutes I have left, or someone can point out the clock?
Go until you.
Okay, thanks. At least some of you are still alive. Okay, cool. All right, so we have these keys. What are these keys? Well, I'll tell you in a second. So I can generate all these keys by applying this weight rotation, this matrix rotation to each of these X's. So I just put there. I use the same weight across all the inputs. How do we call this one? Do we know? When you reuse the same weight across every input. Weight sharing, okay? What is the architecture by definition that is using weight sharing everywhere? Exactly. So if you ask Jan, that's a convolutional module, but okay. All right, sweet. So we have this case, and then I do the same. So here I get my capital K, and I do the same for these values. I have another rotation for my X's, and so I can apply them to all my X's, and I have this capital V. And so what do we do now? So here I have this other rotation, and I have my V. So now I can do the interesting thing. So remember, K is a vector. Capital K is going to be a bunch of vectors. I take the bunch of vectors, I flip them, I have a bunch of rows, right? And I have a bunch of rows, and I multiply by the single vectors. What happens here? Which of the three representations are we using from the previous slide? From the slide, I show you linear matrix vector multiplication.
We did the average of matrices.
I have multiple, no, I have a single Q. I just multiply, I take I do the projection, right? I do the projection of the single Q against all these rows, right? And so what is going to be this stuff? So let's say Q is going to be how to make parmigiana, the one with the eggplant, right? Okay, cool. So I have how to make parmigiana, and all my other one are the title of the recipes I can make. So I can make parmigiana, but also in US we have something called chicken parm. I know, I'm in Italy, I shouldn't, this is blasphemy, right? Okay, but anyway, we have chicken parm, which is also parmigiana somehow, right? We are so near to Parma, they're gonna kill me. But anyway, sure. So I have this question, how to make a parmigiana, and this is gonna be comparing the question with all the title of the recipes. There are two hits. There is a big hit for my actual eggplant pasticcio, whatever, a lasagna. No, it's not without lasagna, it's pasticcio. And then the other is going to be the hit with the chicken parm. All right, sweet. I have this bunch of scores. Two of them are non-zero. The other one are, kind of tiny. Sweet. I have this multiplication, and I get now to convert these scores into these attention fast weights, these kind of probabilistic things. And so what do I do next? I just do the last one, which was the capital V times the A. this was the second one, the weighted average. So my C, which is going to be my context-based summarization now, is going to be the average value, a weighted average, because attention is just weighted average. Okay, we got it there. All right, sweet. So here we have this weighted average, and what happens now if I take any of those x's in the big X and I flip it? What happens if I take the second x in the big X and I flip it with the third x? What happens to C? Okay, what happens to the K's if I flip two of the x's in the input? The K's also will flip, right? And so, how about the V's? Also, the V's will flip the same way. Okay, and so my weights with my attention coefficients will also have flipped. And so when I take the weighted average, although I flipped two items, but also the coefficients just flipped. And so regardless of how many times you flip shit around, you're going to get still the same weighted average, okay? And so it turns out that C is going to be some fancy term, permutation invariant. Because regardless of whatever you flip around, C doesn't give a beep. And so this is very interesting, because if you have a set doesn't have order, neither this stuff has. This is going to be building a representation on things. You can permute the order. The representation is still the same. Now, second question. How about I use on the left-hand side, this is left, right? No, on the right-hand side, this is right? On the right-hand side, you have a single x. How about I put all the x's there? So I put all the x's, how many c's do you have? You have as many c's as I have the x's. So now if I have capital M x's on the bottom side, I will have capital M c's on the top. What happens now if I flip the order of these x's? The c's also will flip on top. And so this is called instead permutation equivariant. So if this is exactly what you want. You have a set. The singular representation doesn't change if you change stuff, but the representation of each thing will change as you start changing things, right? Okay. And so this is why self-attention is a set representation, is a representation for sets. Why do we care? Okay, next slide. Before why we care, I can tell you why we care. Let me tell you why we care. So why we care about that? Because we can move from sets to sequences in a very simple way. So self-attention is defined over sets of vectors, but then a sequence can be casted as an augmented set, where you specify not only the specific vector item, but also you add the embedding for the positional embedding. You're going to be adding information for who are you, right? Although I have a bag of potato, but if you label each potato, then you can still consider a bag of potato a sequence of potatoes, because you can still go and look at the number. And so that's why it's pretty convenient to have a set encoding, because you can basically encode anything you want, as long as you specify the coordinates. This is very powerful, actually. Let's say you want to do like protein folding or atom labeling, something. As long as you provide the coordinate of each atom within the actual vector, the system can actually handle any geometry, right? So the set is going to be the loosest representation. Anyway, let me go back to self-attention. Pay attention. I will be going to flip between two slides and then see what changes, okay? I go forward and back. Forward and back. So the title changes from self to cross-attention. And the only thing that changes is the first line. The X become a Y, which is the target. And then the picture on the bottom right-hand side has the only single item changing from X to Y. So that's the only difference between self-attention and cross-attention. You're cross-attending from a different side. What is Y? Still me looking for making parmigiana. Who's X? My mom. She has more recipes than I do. So I call her and I check my own single question, how to make parmigiana against her own recipe book. How many recipes mom has? Many. My mom can cook a lot. So she has many keys, way more many keys than I do. And so I still do the question, like, I want to cook this, I'm hungry. She's not hungry. I mean, she can be hungry, but she's not going to call me to how to cook things. So I call my mom with my same question, how to make parmigiana, and she's going to tell me what is the matches with her recipe book, and then she's going to be providing back the recipe. Cross-attention. Finally, how do we get to the transformer stuff? Well, transformer is going to be just a bunch of these self-attention and cross-attention with the following architecture. So I have my X, which is going to be, again, connecting back to the machine translation case. It's going to be my source sentence. I have an encoder, which is encoding my source sentence. On the other case, I have my target sentence, which I delay by 1. Remember, we'd like to have this delayed target such that we can predict the next word. I have my, I showed you before this, the delay unit. I have an encoder for my target, and then I provide those two things inside this predictor, which is going to generate the hidden representation. And then the hidden representation can be decoded in my y tilde, which I make it close to my target, again, with this cost. And so this is the transformer architecture, which has correct names. It doesn't have the wrong decoder. Unfortunately, on the paper, they call the decoder everything that is in that box. As you can clearly see from the diagram here, the decoder goes just from the hidden representation to the target. At the beginning, I have to get my inputs. I have to encode the inputs. I have to mix the inputs into this kind of mixer, which is called a predictor. After I finish the prediction part, I had to decode it to be able to spit it out in the target space. And so this would be the correct way of looking at things. But again, I can say what I want. No one is going to complain. Anyway, so X is going to be the source sentence, Y is going to be the target sentence, and then the Y tilde is going to be the predicted sentence. So let me open up those boxes. What's inside the encoder? The encoder has the self-attention, which was the set encoding mechanism we saw before. And then there's a one convolution. Yes, I know, they call it feed-forward network with weight sharing. We're for convolution. Anyway, so then I have this addition and norm, and then addition and norm. What's inside the addition and norm? Just a residual module with the layer normalization such that things don't explode. And then I have these connections. Amazing. So I input here my source sentence, my X, my mom set of knowledge, which can be converted into values and keys. And then I have my final hidden representation, this kind of condensed self-attending item, which is allowing us to why is necessary self-attention? So, for example, this is a question that came up in my class recently. It's like, usually we use word embeddings to have vectors that are reflecting somehow the meaning of words, but then it turns out that some words have multiple meanings. For example, the word rose. I gave my mom a rose, or in this morning, the sun rose. So it makes sense to have a vector that is representing the same rose? No, it makes no sense, right? Rose, flower, rose, the sun rose, has no whatsoever connection. So there are accidents in natural languages that are basically same words having completely different meanings. But now we have to use vectors that are going to be representing the meaning of the word. And so you should have as many vectors as the meanings. Who decides what's a meaning, right? What do words mean? Distributional hypothesis, co-occurrence of words, blah, blah, blah. You can look it up on Wikipedia. Yes, we don't even know what words mean, right? So words are acquiring meaning just based on the usage that you make, right? I can come up with a gibberish word that I keep using it like soft argmax. Eventually, you're going to trust me, that's called soft argmax. Right, so this stuff here, instead of having, we start with single vectors for the tokens, for the words, but then as we use self-attention, each word will build up a representation which is depending on the context in which you find a word. And that's why we talk about contextualized word representations as better vectors representing the meaning of specific words. So this is why self-attention has some utility. Anyway, this was just a parenthesis, parabola. Let's go back into our module here, and let's have a look at the correct decoder. Well, no, actually, the wrong decoder. Wrong decoder has this stuff inside, and so it has the cross-attention. The cross-attention is attending to what? My mom, right? So it's going to be sourcing information from the source sentence from the keys and the values from the question in the target sentence, how to predict the first word. Which was the first word? Remember the sentence? La porta d'ingresso è rossa. Now we have to predict la. And so to predict la, I have to look for, oh, can you give me the hidden representation of the first token, which was the. But then I don't know the gender of la. So also I need the token hidden representation for porta. And so by catching those values from, given that I match with the keys of those words, then I can figure out, oh, maybe I can, this is my hidden this is the information I get from the source sentence. Now I can build my word representation that is going to allow me to predict a y tilde close to la, which is going to be the correct prediction. So here we have, again, this addition. And then here, they call this decoder. Again, I would argue, okay, I will argue in a second. Here I put my target sentence shifted, and then I force to predict the next word on the top. And then how do I generate things? I feed back. So one important part here, then I finish, is that during training, we use something called teacher forcing. I will force the correct translation at the beginning of the model. So I provide the whole input to the model. I provide the source, and and then I provide the target. Everything is provided. I just have to compute a bunch of matrix multiplications. I have all the outputs at the same time, and I just try to minimize those distances, those costs. And then everything is just a matrix multiplication. And so everything is just parallelizable. There is no recursion anymore. You don't have to wait for the previous operation to end before starting the other one. You can start from the last word if you want, or you can do all of them together. It's a GPU. It doesn't even care, right? And so this is why this architecture really took off, because it's going to be highly parallelizable. You can just train everything teacher forcing. But then, of course, if you have to use it, well, if you have to use it, you have to say a word, then you feed the word back. You can output the second word, and you feed it back. You get the third word. Then you still have to use auto-regression for generating things, unless you want to use the new diffusion text model that are generating text starting from the end. I don't know if it makes any sense. Anyway, so the point here I wanted to make, then I'm done. This doesn't look like a decoder, because the decoder has inputs coming from the other side. So I would argue that the bottom side, the self-attention, is the encoding part that is looking at yourself, is self-introspective part. Then I'm combining my self-introspective work with your self-introspective work together with this predictor that is mixing those two flows of information. And finally, when I got something out, then I feed this to my decoder to produce the output. And so eventually, we're going to be training these huge models on basically the whole internet text that has been ever written. And so this pre-training is going to be the stage where we acquire knowledge from whatever humans have written on the cyber web. And this allows us, we train them either with masked language models or next word predictions, most of the time next word prediction. And then finally, we have to make them useful, because otherwise, these models, if they are knowledgeable, doesn't mean that they are useful, right? You can have professors that are winning Turing Awards, and they're very knowledgeable, but arguably, might not be very useful. But then if you fine-tune them to meet your own expectation, then they can actually do something that is useful, right? So whenever you force them to actually steer their behavior, so this is called alignment. Whenever you use techniques to improve the instruction following capabilities with respect to certain objectives, for example, like helpfulness or harmlessness, right? And so again, the whole overall big picture is going to be we remove recursion, we introduce recursion to be able to deal with variable length. Then we said, oh, just fuck it up, just fuck it off. We just going to use weighted average for attention. And then finally, we have put together a lot of attention layers, train the system on the overall every internet data, every internet textual data we have. And then finally, useless but knowledgeable items, we just steer their behavior to be somehow useful. And that was pretty much how we went from classification to conversation. Thank you for listening.